So guys, this is the very last little interaction we're going to have together, virtual as it is. So it's a little bit sad, a little bit sadness creeping in here, but maybe a little bit of relief as well. So this nightmare is over. So I want to finish with this thing called Bayes' theorem, and it's I'm afraid it's a little bit half-assed what we're going to do here, because I'm not going to show you any applications of Bayes' theorem in data analytics. But I definitely need to show you this because this is a very, very important tool in the data analytics world. And so it would be very remiss of me if I didn't at least show you where Bayes' theorem comes from. But as I say, we just don't have time because of the fact that we've got this online kind of interaction thing which slows things down, and the fact that the term has been curtailed a little bit this time as well. So because of all these two kind of constraints, I can just introduce you to Bayes' theorem. But Bayes' theorem is a very, very important little technique. If you do actually get into this stuff as a professional, you will come across it. It's probably one of the more basic tools that people use. It has a similar status, I suppose, as regression. Regression is kind of straightforward, very simple, but very, very powerful technique. And that's exactly the same as Bayes' theorem. And I just wanted to introduce this to you because it is very powerful, and many people in the data analytics world are not very comfortable with it because they're not comfortable with statistics and probability in particular. And I just want to encourage your comfort levels, or raise your comfort levels with probability, because probability is very, very straightforward, right? It's a basic definition, a number of things you're interested in over the total number of things. And that's all it is. It's that very, very simple definition. Okay, and I just want to show you how it's used in a kind of a little bit of sophisticated kind of situation, but not too sophisticated. Don't run away from this. Okay, let me just use an example. There's a very famous database in OR. It's built in, and it's admissions data to UC Berkeley. And the categories are gender, male and female. Although when you think about Berkeley, maybe that's a very, very prescriptive two categories there. I'm sure these days there's a lot more. But this is the way the data. This is from the 70s. So in those days, people were either male or female, or labeled as male or female. And also whether or not they were admitted or rejected. And this database is famous because it was formed the basis of a court case, because some people thought that there was discrimination on the basis of gender going on in the admissions of UC Berkeley. Okay, so this was the basis. So this does have real life applications. This was argued in front of judges, although that's a bit scary in and of itself, because judges, when you think about it, got 40 in a set of exams in UCD and weren't really that au fait with probability. So that's neither here nor there. So the data set, I'm going to call it UCB, just for convenience. But it's UCB admissions. Okay, so that's the data set. So let me just show you what UCB is. So if you look at this data set here, there's data for 1, 2, 3, 4, 5, 6 departments. And for each of the departments, there's a gender breakdown and there's an admittance breakdown, whether people were admitted and rejected. Okay, now if you look at the structure of UCB, and this is another reason why I want to do this before we end the course, you see that that the UCB data structure is what's called a table. And a table essentially is kind of a multi-dimensional matrix. Okay, so if you just have a 2x2, or if you can represent the data in terms of just two categorical variables, then you might use a matrix, although you can't label the columns. Okay, but if you have a multi-dimensional, as here, because when you think about this is a three-dimensional data structure, because we've got data for each of the departments, and then we've got gender data and we've got admittance data. So there's three variables going on. There's three dimensions in this data structure. And so therefore this table structure is a very, very common data structure as well. Now we're not going to do much with it beyond just very simple calculations involving probability. But another reason why I'm kind of keen to finish with this is just to let you know that in addition to vectors and data frames, there is a multitude of other data structures that if you do get into this stuff, you will see. Now, the problem with tables and matrices, but tables in particular, excuse me, is that the, I'm choking here, the excitement. I'm okay. Is that the operations that you can perform in tables are different to those that you can perform in data frames and vectors. So operations that work naturally with data frames and with vectors don't work naturally with tables. And so tables have their own little groups of functions that you use. Okay, and that's basically it. Now, we want to look at probabilities, folks, because if you remember, the whole point of this was there was a court case brought on the basis of a sex discrimination, that somebody felt that that Berkeley was discriminating against females because the admittance rate for females was lower than the admittance rate for males. And so they seemed to think that there's on the face of it, there's a prima facie case for discrimination. Okay, but to analyze probabilities and when you're talking about tables, you have to use what's called the add margins function. Now, add margins function is specific to tables, and what it does, it sums up all the rows and all the columns and gives you grand totals for each of these 6 data sets here, or these six tables here. And in addition, it gives you the total of a total data summary independent of departments. Okay, so I made a mess of this when introducing it, but let me just show you what it is. So as I said, guys, tables have their own little, occupy their own little corner of the data analytics world, and the functions that you use in tables are different from data frames and vectors usually. So this is one example. Okay, so what you see here, guys, is what this does. It adds up all the rows and all the columns and then gives you a grand total for each of the departments. And then right at the end, and this is the one we're going to use, this one here, it kind of puts all the data from all the departments together, and it kind of generates a gender admittance type table for all of the departments in Berkeley. Okay, and that's the one we're going to use. All right, now you need to be able to maybe subset each of these tables, and in particular you want to subset the last one. And so what I'm going to do now, guys, I want to call the add margins data set. So sorry, guys, I'm losing touch of reality here. If you look at the structure of the output from the add margins, you again get a table. So add margins takes a table and it outputs a table. Now, we want the last table here. If you look at this one here, we want the departments summed. We want the grand totals, okay? Because we're interested in the effect of gender on admittance, okay? And in fact, that was the point. That was the mistake that people made actually in doing this. But for the purposes of just introducing Bayes' theorem, we're just going to look at the last one here. Okay, so I'm going to call this table here. I'm going to call it TT, total of totals or something. I don't know. So I'm going to call it TT. Now, we know that this table here is a subset of add margins. So I'm just going to write in add margins and UCB. So that's a table, right? Because we know that that's a table. Now, what we want to do, guys, is and if you look at the department in the structure there, you see the department is the third variable. So just to get all the rows and all the columns, But and this table down here is the 7th table. If you count back down, look, 1, 2, 3, 4, 5, 6, 7. So the department summed table is the 7th element in the 3rd part of this table. So just to get that on its own, you have to type in comma, comma, and then 7. Now the first comma, it gives you that's the first part of this function here. That refers to the admittance. The second one there refers to gender. Now we want all of those, so we just put in nothing, and then we type in 7. Okay, so if I just type in TT now, I get just the table from the total. So I'm just doing this again, guys. Is this important? No, it's not. But I'm just showing you that if you want to kind of, again, like data frames, being able to splice and cut the output from tables is really, really important. And this is just one example. Now, it's not easy with tables, guys, when you're doing this. And this is just one situation where it is easy, but it's certainly not intuitive that this is how you do it. And this is only one way of doing it. There are many other ways of doing it, but this is probably the easiest way to do it. Okay, so what you're doing is you want the department sum table. You know it's the 7th one for the third in the 3rd argument essentially of the add margins UCB. So it's comma comma 7, and the reason why you don't have you have nothing in the first 2 arguments is because you want all of admittance and you want all of gender. Okay, there you are. That's how you do it. Now, folks. The great thing about what we talked about, you've talked about this with Abdal, about probability. Okay. Now, once you have a table like this table where you've got all the data, you've got 2 categories. In this case, it's our 2 factors. You've got 2 categories. You've got gender as one category or factor, and admittance status as the other category or factor. And in this case, guys, in each of those 2 factors, you've got 2 levels. You can have more than 2 levels. You can have as many levels as you like. But in this case, though, you've only got 2 categories or 2 factors. Okay? Gender and admittance status. Now, we want to analyze this using probability. We want to extract some useful information because remember, the probability can act as a kind of a summary measure. Okay, so what you can do is you can do all sorts of things here. Now, I'm going to type in what I want here first, and then I'm going to actually use R to calculate it. But look, I'm going to type in, suppose I want the probability that a student who applied for admission was male. Okay, so what's the probability that an applicant was male? Well, what do you do? Well, it's the number of things you're interested in over the total number of things. What's the total number of applicants? It's 4526. So you should always do that first. That's the total number of applicants. And of those, how many are male? Well, you see it's 2691. Okay, now get an error there because P brackets M means nothing, right? But if you want to calculate this, guys, you just do 2691 over 4526. Yeah? No, that's the way you go. So that's the probability that an applicant was male. To get the probability that an applicant was female, then you can subtract that from 1 because an applicant is either male or female in this case. Okay, so that's what you can do, or alternatively you can write it as 1835 because that's the number of female applicants divided by the total number of applicants, which is 4526. There's a number of different ways of doing this. Okay, now I must admit that I always feel a little bit grubby doing this, where taking numbers that I can see and typing them into R. I don't know why this is. I much prefer being able to actually use the variables that these numbers are in. So for instance, instead of writing 2691 over 4526, what you could do, and it's a little bit fancier, but it's not at all necessary, you get exactly the same answer, is, okay, we've got the TT is the table that we're interested in. We want the number of males, which in this case is in the 3rd row and the 1st column. Okay? So we want TT brackets 31. So that tells you take the number in the 3rd row and the 1st column. which I think is 2691. And then you want to divide that by the total number of applicants, which in this case was 33. So, so what I'm doing here now, guys, is I'm accessing the numbers using their location in the table. Now, again, do you have to do this? You don't have to do this. But I don't know what it is. Some part of me kind of doesn't like just for copying numbers and pasting them and dividing. I don't know what it is. So, so you get exactly the same answer, right? But this, I suppose, the second way that I did it is a little bit more sophisticated and a little bit more general. So if you changed the table, you would get this different answer, but it doesn't matter. All right, I'm just saying this is just my own neurotic self here. All right, so you can do all sorts of things here, guys. All right, so you can get what's the probability that a student was admitted. Okay, so probably a student was admitted. Well, what do you get? What's the total number of applicants is 4526. How many were admitted? Well, you see it's 1755. All right. Okay. Again, so this is what you get. So the probability of admittance was 0.38. Very good. And then, guys, what you can do is you can, again, you can maybe use the addresses of the variables within the table. So to get 0.3877596, the more sophisticated way would be to do it. It's in the first row, third column, and then it's again. So you get the same thing again. So it doesn't matter. Now, one of the reasons why I'm doing this is I want to kind of emphasize the whole notion of probability, how easy probability is. But again, just showing you how you can access individual elements of a table. Okay, because again, you know, if you start getting into this stuff, you will be messing about with this. Okay. Now, finally, guys, there's a few things there's one very, very important thing that I want to talk about, and this is the thing called conditional probability. Now, we've talked about probability, a number of things you're interested in over a total number of things. And in conditional probability, that's exactly the same. But the only difference is that the total number of things is changing all the time. Okay, so I'm going to type this in R. I'm just going to type it in here, and of course, it's not going to do any calculation. But let me just ask this: what's the probability that a female student? Okay. So what I want now, guys, I want the probability that a female student was admitted. Now, here you have a condition. And the condition here is that the person that you're interested in, or the thing you're interested in, is female. Okay, because thing in general, but person here. Okay, sorry. You have to be very careful these days. All right. There was no offense meant. Because in general, you're not going to be talking about people. You could be talking about parts and whatnot. Okay. So if you look at this probability here, this is different from the probability that a student was female, or the probability that an applicant was female. Okay, because the probability an applicant is female is the number of females, which is 1835, divided by the total number of applicants, which is 4526. Now, in this case, you've got a condition. You've got a subset of the total data here that you're interested in. Now, in this case, you know that the student is female. Okay, so the probability that a female was admitted is, in this case, guys, the total number of things is not 4526, but it's conditioned on the fact that the student is female. Now, how many female students applied? It's 1835. Okay, of those 1835, how many were admitted? 557. Okay, so conditional probability is telling you, don't look at the full table, but look at either a row or column of the table. There's a condition. And sometimes, guys, it's difficult to recognize that there's a condition. Sometimes you can see the words if or given that, they're giveaways that you've got a condition here and you have to use conditional probability. And so here, this is not obvious. What's the probability that a female was admitted? The condition here is that the person applying was female. Okay, very good. Now, boys and girls, let's look at the kind of converse problem. Okay, so I'm not going to, you can type that in here. So now, guys, you have to be careful with this because sometimes, here's a different condition. Here's a different problem, although it looks very like the problem we've just done. What is the probability that an admitted student was female? No, not the probability that female was admitted, but the probability that an admitted student was female. Okay, so this is where it gets, it's the language causes confusion. That's where it is. The mathematics is very, very straightforward, guys. It's exactly the same definition of probability that Abdel introduced. Number of things you're interested in over the total number of things. It's just that the total number of things needs careful identification. So in this case, guys, what you're told, the condition is that the student was admitted. Okay, so how many of those are here? It's 1755, and of those, how many were female? 557. Okay, so in this case, instead of looking at the column, we're looking at a row. Okay, so what's the probability that an admitted student was female? It's 557 over 1755. Okay, and this kind of idea of conditional probability is extremely topical at the moment, guys, because of the COVID vaccine introduction. And this is what they did. Essentially, this is what they ended up with. Now, they I don't know, deliberately make it more complicated, but basically what you have, instead of male and female, you've got vaccine placebo as one category, and the other category is got virus, didn't get virus in the other category. And so what they're interested in, I suppose, is what's the probability that you don't get the virus if you got the vaccine. So conditional probability is extremely crucial concept in data analytics. And okay, so that's what I want to introduce you to. Now, let me just do one further thing, guys. One last thing. Okay. Now, I'm going to do this. Okay. Oh yes, notation. Probability female was admitted. Can I just take this here? Again, no, guys, I'm not doing any I'm just typing here, right? In statistics, a probability that a female was admitted is written as, the notation for it is very specific. Now, what do we know? What's the condition here? What is given to us? What is given to us here is that the applicant was female. So the condition always goes on the right. You put a straight line down the middle, and what goes on the left end is the condition, is the thing that you're interested in. In this case, you're interested in the admittance. So the probability that female was admitted in mathematics is written as P brackets A given F. So that bar is written as given. Okay. In the second situation, guys, there, the probability admitted student was female. In the shorthand for that is, as you might suspect, the other way around. So I just wanted to do, I wanted to again also to introduce you to the notation, because that's important. You would see it and you'd be wondering what it is, and it's just nonsense. When I was your age and I saw this notation, I was a bit frightened because I didn't know what it was. And in fact, a lot of mathematics, guys, is that it's just a notation that they invented for something that's fairly straightforward. And then you get lost in the notation. You just don't know what the notation means. There's no mathematics involved here. This is just shorthand. There's no mathematics. Sorry, guys, there's a P missing here. Okay, so this is not mathematics. This is just shorthand, literally just shorthand, a quick way of writing what's on the left-hand side is written on the right-hand side. But the important thing that you have to remember here, guys, is that on the right-hand side of the bar is the condition. What do you know is true about this particular object? Okay, in this case, again, guys, we know, yes, in this case, in the second case, we know that the object was admitted. The applicant was admitted. So we know that the thing that we're interested in is the admission. Okay, and so therefore that goes on the right hand side. And of those admitted students, we're interested in the number who are female. So then you just get that. Okay, but again, guys, let's not forget, the most important thing here, guys, is the application of the basic definition. The basic definition still holds here. But you will notice in these two cases here, in case 1 and case 2, the total number of things is different. Okay, sorry guys, I just got lost in thought there. Okay, now last thing. If you look at these numbers here, guys, there's a relationship between all the different things. Okay, now if you just look at the numbers, if you start messing about, if you look at these things here, you will see that if you look at the numbers here, okay? If you look at the numbers, if you just look at these numbers here, if you calculate the probability of female given admittance by the probability of admittance, it's exactly the same as the probability of admittance given female by the probability of female. And it's true, this relationship is true, regardless of what the numbers actually are. Okay, it's always true. Whatever the categories are, whatever the factor levels are, you will always have this relationship. Okay, so it's just basically numbers. The numbers, this is the way the table is set up. Now, it's not obvious that that relationship is true. And the first guy to discover this, or the first guy to come across this, or to see that this relationship holds, was a guy called Bayes. And this theorem is called after him, it's Bayes' theorem. And it's actually very, very clever. You know, when you think about it, okay, you think, oh yeah, of course. If you go back now and look at the numbers, guys, you will see it. One number is equal to the other number. You think, oh yeah, okay, it's no big deal. But the insight actually is quite remarkable, because this is the simplest things are the most intelligent, you know, the smartest, you know, that's you know, if that's something that's not obvious, is what I'm saying to you, that you've got this nice relationship. And this nice relationship here, guys, is called Bayes' theorem. Okay. And it's not really a theorem, because, you know, you don't prove it, because it's always true. It's just a statement of fact about these tables up here, guys, are called tables, but in statistics, because you can't call a table because everybody would know what that is, in statistics they're called contingency tables. But this fact here, this last line here, is a basic fact about every single contingency table. In this case, we're talking about female and admittance, F and A. We could talk about male and rejection, or you could talk about male admittance and female rejection, and whatever. Yeah, it's whatever the two variables that you're interested in, or two events that you're interested in. Okay, you would get this relationship. And guys, usually, if you look at this relationship here, in practice, you will usually know 3 of these 4, depending on what, you know, in practice. Okay, now in this case, we know what they all are. We know what each of these 4 things are. But in reality, life doesn't come as a simple contingency table. Usually, what happens is you will know 3 of these variables here. So typically, you know what P of A is, you know what P of F is, and you know what P of A given F is. Let's go with this. You don't know what P of F given A is, okay? And you want to make a prediction about that. And so if you want to find out what P of F of A is, you just divide both sides by P of A. Now, guys, if I can come down here and just do that. Again, so I'm just using this as a sorry guys, I'm just using this as a word processor here now. All right. And this is the most useful form of Bayes' theorem. Because as I say, guys, in practice, when you're actually using data, typically you will know 3 of these quantities. And let's say you know those 3 on the right-hand side. And so therefore then you're going to use Bayes' theorem to get the 4th. And all Bayes' theorem is, folks, when you think about it, is just the way numbers are put together in the table. That's all it is. People don't like this in data analytics because people are always afraid of probability. My advice to you guys is don't be afraid of this if you get into this game. And this is a very, very useful tool in data analytics. For instance, just give you one example and I'll stop here. For instance, if you're using a filter for spam or something on your email, this is the way that spam filters work. Well, this is the way that some elementary spam filters work. By using the Bayes' theorem. It's quite remarkable. And it's very simple, but it's very, very powerful. It's like regression. So as I said to you guys, I wanted to introduce you to it because it's a very, very basic tool. Unfortunately, because of time constraints, I can't do any more than this, and I'm going to leave it there. Okay? Thank you very much.